Hello, this video is entitled Vectors in the Plane. Now some of you from experience in physics, whatnot, will already kind of have an idea about how vectors in the plane work. So this video may not help you that much, teaching you something you don't already know. But for those that haven't had any experience with working with vectors, hopefully this will be useful for you, because vectors are definitely used a lot in Calculus 3. So first thing we're talking about, a vector is essentially a directed line segment. Directed meaning, of course, direction matters. And where we have an initial point to a terminal point. And this would be called vectored PQ. Some books use boldface for vectors, but that's when you're writing it out, it's hard to indicate boldface. But if you can see there, or an arrow right at top of that PQ indicates that it's a vector. So if you took that same line segment and reversed the arrow from Q to P, that would be vector QP, and technically it's a different vector. Now, one thing about vectors, if they have the same length and direction, they are equivalent vectors no matter where their initial and terminal points are. Meaning, vector, the idea of vector, we'll talk more about that, they can kind of move around. And you'll see when here in just a minute how that works. But these are, if they're all the same length and same direction, they are equivalent vectors. They're the same vector. They just have a different starting point and finishing point. Okie doke, so let's see what we got here. And there's where I mentioned about the boldface, or the kind of arrow, partial arrow on top. Now there's two types of forms of how vectors can be represented. The first one we're looking at is called component form. So definition of a component form of a vector in the plane. Now they're using boldface here, B, and they're using these angled brackets. So we do not confuse this with parentheses. Parentheses only means for point locations, and we'll talk about that here in a minute. But angled brackets mean you're talking about vectors. So angle bracket V1 comma V2 is defined here as vector V. And the coordinates of V1 and V2 are called the components of V. Now there is such a thing as a zero vector, which seems kind of weird, you know, the idea of being a zero vector, but it's denoted as boldface 0, and it would have components 0 and 0. All right, now let's suppose we have this example of a vector 3 comma negative 2. Now, you know, like that previous picture on the page about the equivalent vectors, you know, showing they can start and finish anywhere. So to plot a vector 3 negative 2, you can start any point, and what this means is the 3 means from wherever you start, that's essentially the x direction, how many units you would go in the x direction, and then the v2 here would be the y direction. So the vector 3 negative 2 means to graph that vector, you go 3 units to the right, positive direction for x, and 2 units down, which is the negative direction for y. So if you come over here, we look at, so I just picked this starting point right there. Just arbitrarily chose it, but if that was my starting point, the finishing point would be 1, 2, 3 units to the right, 2 units down. If I start at the origin, it'd be 1, 2, 3 units to the right, 2 units down. And those are both equivalent representations of V, vector V. Now suppose you know two specific points that you want a vector, that the vector is going to go through. And say P is defined as P1 comma P2, a point. Point Q is Q1, Q2. And to figure out what would be the vector V that's represented by vector PQ, so you see here's the component form with the angle brackets for the vector. you take the first x minus the second x, q1 minus p1, then you take q2 minus p2 to be the y component of the vector. All right. So you just subtract. So that's pretty easy. All right, suppose we have a starting point of p of -2, 3, and then q is 1, 2. Let's find what pq is and what qp would be, the other direction. And those are two different vectors. So pq means you take the first component of q, or the first x value of q, component means vector, excuse me. So it'd be the 1 minus a -2, and then 2 minus 3. So 1 minus a -2 is 3. 2 minus 3 is -1. Now QP, you'd reverse them. So Q to P means P is the terminal point. So you take -2 minus 1 is -3. And you take 3 here minus 2, which is 1. Now notice that these, from PQ to QP, these just have opposite signs. That was not coincidence. In fact, we'll probably see that defined coming up here shortly. But yeah, the vector going in the opposite direction is just, you just take the negative, the opposite sign of each component. So for example, if you had a vector v called 3, 6, that means the negative of vector v would be -3, -6. So reversing the direction essentially makes it the negative of the vector. Length or magnitude of a vector. And this formula kind of comes from, well, two things, Pythagorean theorem, and also the distance formula between 2 points. So essentially, it's if you drew a horizontal line segment and a vertical line segment, it would be the hypotenuse of that right triangle formed by those components. So if it's in PQ form, as in 2 points, you would take the square root of Q1 minus P1 squared, which is the x component, Q2 minus P2 squared, which is the y component. Or if it's already in component form with V1 and V2, you just take the square root of V1 squared plus V2 squared. And now we have another definition that says vector V is called a unit vector if the length of V, length or magnitude, is 1. And we actually use that for other stuff coming up here, so that idea is important. And then I'm showing you P. Okay, I've already figured out. We figured out that PQ was 3, -1. So its length would be, its magnitude length would be, right here, it would be 3 squared plus -1 squared. So that vector would have a length or magnitude of square root of 10. Now in vector terminology, when we say scalar, that represents a numerical value. And we'll talk about how that's used, how scalars and vectors kind of work with each other. All right. So now let's say, suppose we have a vector here, v is given us 4, -5, and we have an initial point 7, 2. Could we find the terminal point from that? Yeah, so we haven't done that, but yeah, we've just been, using initial point and terminal point to get the vector v. But essentially, it's like 3 variables, and if you know any 2 of the 3, you can get the third one. So I just set this up as saying, okay, the terminal point, which is unknown, minus the initial point would equal 4, -5. So basically, it's taking, so if you move this over, 4 plus 7 would be 11, and then -5 plus 2 would be -3. And you could double check that. You can see that 11, -3 minus 7, 2 would give you 4, -5. So that's not too difficult. Now here are some vector operations. So let's say we have vector view, u is denoted in component form as u1, u2, and v is v1, v2, and we'll let some c here be a scalar. To add two vectors numerically, it's really easy. Just add their components. So to add u plus v, you'd have u1 plus v1, comma, u2 plus v2 to get the second component. Easy enough. A scalar multiple times a vector. If you have a number times a vector, you just take that number and you basically are distributing it through the vector. You would just multiply each component of the vector by whatever scalar multiple that is. Okay, the negative of a vector, we talked a little bit about that before, but that's essentially multiplying the vector by -1. So the negative of v1, v2 would be negative v1, negative v2. And u minus v would be actually, you can subtract the components, but when we show you geometrically here how to add vectors geometrically, it's better to convert it this way, but numerically you don't have to. You see it still ends up being u1 minus v1 and u2 minus v2. But yes, u minus v is the same thing as u plus a negative v. They're not really defining subtraction as its own thing. They're just saying add a negative. So one thing to keep in mind, you can multiply a vector by a scalar. You can't add a vector to a scalar. Can't do that. That's not a valid operation. So let me sort of mention. And the result, of two vectors being added or subtracted is always a vector result. So just for a second here, let's pretend like that u and v were the same vector. And I went u minus v. Well, if they have the same components, each component's going to be 0. However, the answer would not be the number 0. You would not say, oh, that equals 0. That would be wrong. It's actually the 0 vector. So it would have to be either be written as 0 with the arrow above it, or just 0, 0 as the component. So you can't subtract two vectors and come up with a number, a single number. It would have to be a vector. All right, this is pretty easy. So u plus v, just add the components. 5 plus 7 is 12. Negative 3 plus 4 is 1. U minus v, I didn't even do it as u plus a negative v, but I could have. I just subtracted. 5 minus 7 is negative 2. Negative 3 minus 4 is negative 7. 3 times u, just multiply both components by 3. So 3 times 5 is 15. 3 times negative 3 is negative 9. And then negative 3 times v, so just multiply both components, 7 and 4, by negative 3, and you'll get negative 21 and negative 12. Now here's what I was mentioning about adding vectors geometrically. I'm not sure if you'll ever have to do this or not, but it's not too bad. It's a neat little skill to know, I guess. Now we've talked about the idea of a vector. Once you know its vector components, that means, you can start a vector anywhere and move it, left or right or up or down according to the components of a vector. So like I say, to add this vector u and v, what you need to do to find u plus v is that v, or either bring the u down or the v up. The v, keeping the same angle and length that it has, moves straight up here and it attaches itself to the end of v. So if you go the initial point of u to the terminal point of u, that connects to the initial point of v to the terminal point of v, and then if you draw a vector from the starting point of u to the ending point of v, that vector would represent u plus v. And that's all you really have to do. Now here's another one. If you brought this vector v up here and attached it to the end of u right there, that right there would be your u plus v. Multiplying a u by a scalar that's other than 1 changes its length. And if you multiply it by a negative, it changes its direction also. So it potentially can change your length and direction. So if you multiply a vector by 2, you then will make it twice as long as it was originally. Now, vector subtraction, to subtract, you actually treat it as adding a negative. So you see where your u and v is here. If I want to go u minus v, I want to create a vector called negative v, which is easy enough. It's right there. You reverse the direction. They did this a little bit different than I would have done it, but it still works. I would have moved this vector negative v right to the end. Well, okay, that's still there. Vector, okay, u, and then attach the negative v. That's it. And then you go up this way for u, negative v over, and then you connect the beginning. Okay, this is right. Connect the beginning of u to the end of v, and then that's u plus negative v, which is the same thing as u minus v. So I'm not sure if you're going to have to worry about that too much, but I think it's good to talk about how vectors are affected that way by adding, subtracting, and scalar multiplication. So here's an easy subtraction problem. We'll look at this next example. See that? You cannot add a vector to a scalar. That's an undefined vector operation. You can only multiply. All right, so here's a bunch of properties that I don't know if you have to worry about knowing all of these really per se, but all right, that one's easy. U plus v equals v plus u, commutative property. Associative property works. U plus the 0 vector. That 0 is a vector. It's bold. It's hard to tell. It'd be better if it had the arrow above it, but it's bold face. U plus the number 0 is meaningless, but u plus the 0 vector will give you the u vector. Same thing here. U minus u is the 0 vector, not the number 0. Okay, this one's no big deal. These are no big deals here. Distributive property. All right, that's all easy enough there. This one, you see that now in front of that vector u, that time that is a number 0. That's a scalar 0. Number 0 times any vector u will give you the vector 0. So the first 0 is a scalar. The second 0 is a vector. Okay. Now let's say that your vector has a scalar multiple something. You don't have to do this, but I like to do this anytime I'm figuring out the length of a vector. It makes it a little easier. This says that say if they shared a common multiple of 5 or 2 or something like that. That means you can pull the absolute value out, meaning if it was a negative 2 or positive 2, that only affects the direction of the vector. It does not affect the length of the vector. So if you factor out a negative or positive, whatever the absolute value, will make that positive. So it's the absolute value of C, then you can find the magnitude, the length of V. But you can do this without doing that, but it keeps the numbers from getting a little outrageous. Like this one. This vector is negative 64, comma negative 80. Especially if you're having to do this without a calculator. It could be really ugly. So I chose to factor out, which is algebraically correct in vector world. I pulled out a negative 16. And that will leave negative 16. That will leave 4 and 5 in here. And you can see that distributes back out to be this vector. So that means the length of that vector is going to be the absolute value of negative 16 times the length of 4, 5. So you just leave a 16 multiple on the outside, and then you take the square root of 4 squared, which is 16, plus the square root of 5 squared, which is 25. And then you have 16 plus 25 is 41. So the simplified version then would be 16 times the square root of 41, without having to do 64 squared and 80 squared. You're working with smaller numbers. So while that's not absolutely required, I think it's an excellent idea to find length of a scalar multiple of vector. Finding a unit vector in the direction of your vector v. To find a unit vector, now u isn't necessarily a reserved name for a unit vector. I want to mention that anytime you see u, a vector labeled u, that it's automatically assigned as a unit vector. There are some vectors that do have specifically assigned names that we'll talk about, but u isn't necessarily, it has to be that a unit vector. So what you're basically doing is you're taking your vector v and dividing it by the magnitude of v, or in other words, taking 1 over the magnitude of v times vector v. So what you've created by doing that, so you take 1 over that magnitude, and of course if the magnitude is bigger than 1, if the magnitude is bigger than 1, you've shrunk the length of the vector, down to make it length. Let's say vector was length 3, and then you just redefine its components to be length 1, but going in the same direction as v. So here's that vector we just did. Suppose I want to find a unit vector. Yeah, obviously that vector is going to have a magnitude way more than 1. So what I did is I took that, what we got in the last problem, 1 over 16 times the square root of 41. And then that's 1 over the magnitude of the v times the v. And now what I did, so negative 64 over 16 is negative 4. Negative 80 over 16 root 41. I mean, it would be negative 5 over root 41. Now, as an instructor, I'm absolutely not picky about radicals in the denominator. They do not bother me in the least. But you may, if you're watching this and you have a different instructor, they may want you to have to rationalize the denominator. But just, I don't care personally. So we've essentially created a vector. You could check its magnitude that it equals 1, but there's no need to. So that vector would have a magnitude of 1, and it's going in the same direction as my original vector. Now, opposite direction, that should be coming up here in a minute, but I'll just mention it right now anyway. And suppose that when you want to find one in the opposite direction, all you would do is just change the signs of your vector. And if it's negative, make it positive, positive, make it negative. So that would be real easy. That's real quick. You get the opposite direction vector. Now here's two vectors. Oh, just another little algebra problem here. Probably could have had that back up with the other ones. That's okay. That's easy enough. So you just take 5 times u minus 2 times w. So take vector u, multiply it by 5, and you get 20, negative 15. Take vector w, multiply it by 2, you get 7 and 5. Makes that 14 and 10. And so 20 minus 14 is 6. Negative 15 minus 10 is negative 25. Yeah, so here's where I mentioned the opposite direction. As w. So w has a magnitude length of square root of 74. So it's 1 over the magnitude of v times 7 root 5. Now here's another thing too. Technically, this first answer I have is correct mathematically, but I went ahead and distributed it anyway though. But that is correct, like that. But it's all whatever the instructor wants us. But it's yeah. But there it is distributed. It'd be 7 over root 74 and comma 5 root 74. Now the opposite direction, you can do it one of two ways. If you leave it in the first form that I wrote, you would, this form right here, you could just change the outside to negative or the inside. You wouldn't want to change both to negative because if you made this number a negative and you made these negative, then you've kind of, negated the process because negative times negative would be positive. But you could just change that outside negative would be fine. Or if you just probably do it in this form anyway, it's probably better. If you have this answer, you just take the opposite signs of each component. And you got it. All right, 48. This problem, this one of the most interesting problem in this section, I think. Now this says we're trying to come up with a vector v who has a magnitude of 2 and goes in the same direction as u. So we're not necessarily looking for a unit vector. There's a couple of ways you can do this, but the easiest way I think to do is what I did here. If we know that v is going to have a length of 2 and it's going to go in the same direction as u, if we convert, because let's say here's what u is first. So u is length 2 root 3 right here. So it's not length 1. But if we convert u to a unit vector, then we know it's going to be length 1 going in the same direction. Well, if we know that v is going to have length 2, we can take the unit vector we create for u and just multiply it by 2, because then that means, you double it, length of 1 will be length of 2. So just multiply it by 2, and that's what we do. So let's convert u to unit vector. We got the magnitude. So 1 over the magnitude right there, 2 square root of 3 of the vector square root of 3, 3. So I divided both those. Square root of 3 is canceled, and you get 1/2. And then actually 3 divided, it's okay if you let the radical on the bottom, but I went ahead and rationalized it, I guess, whatever reason this time. But 3, I just saw that 3 divided by square root of 3 is square root of 3. And then the 2 is on the bottom. Now that vector has magnitude of 1. And so to get 2, like I was saying, just multiply this vector times 2, and that will be vector v. I could have labeled that as vector v, I guess, but that's all right. So there we go. That's a little tricky. Sort of doing this without using a mouse instead of a tablet, writing on a tablet. That looks all right. So there it is. That would be it. 1 comma square root of 3. It's going to be twice as long. I mean, it's going to have a length of 2, and it's going to be the same direction as u because it's just a multiple of u. Remember, any vector that's a multiple of another vector will go in that same direction. Here, I just showed another way to do it. I won't go through this one, but I'll leave it there so you can kind of look at it. I just sort of set up a common idea and made them both unit vectors, saying that, okay, like ratio, proportions, u is to the magnitude of u would be the same as v is to the magnitude of v. And then I had all the 3 components, and then there was the v I was solving for, cross multiplied, divided it out, and got the same answer. So that would work also. Because if you set them up like this, you're saying unit vector u, unit vector v, they are going to equal each other if they're unit vectors. And there we go. So that would also work. Now the last idea in this section, as I mentioned earlier, the component vector form is one way to write the vectors, but there's another called standard unit vectors. Now these two have to be these. You can't use these letters for anything else vector-wise. I mentioned that the vector u itself doesn't have to be a unit vector, because you might see problems where they just give you a vector u to maybe define vector u plus vector v, and u doesn't have to be a unit vector. But these two vectors are absolutely specific reserved names, and they are both unit vectors. They are called standard unit vectors. Vector I is component form 1 comma 0. So that means it would just go 1 unit to the right anywhere you draw it. So obviously that has a length of 1. And 0 comma 1 means j just goes 1 unit up from wherever you're starting from. So now vectors can be written 2 different ways. So component form 5 comma negative 2 would be the same way as writing the vector as 5i minus 2j. And here I showed the math over here that why that is right. I put in what you would never have to do this, but so I'll put the I and the J in there to show that that was correct. And here's an important note from Stewie. Stewie says, don't ever do this. Sometimes people might think, oh, I'll cover my bases there. I'll put the I and the J, and I'll put components or form around it. Let's give it more, as much as possible. No, that's a wrong way to write a vector. If you're using standard unit vectors with I and J, you don't need any bracket notation or nothing goes around them or anything like that. It's just 5i minus 2j. That's it. All right, if we have a vector v, and we have a certain magnitude and forms an angle theta with the positive x-axis, now I can see where this would have a lot of physics applications, especially when you're trying to find, resultant forces and stuff like that, the force in the x and y direction. I see a lot of use for that. Now, I wrote this in both standard unit vector form, and component form, both. So the vector v, let's say, you had the length or magnitude often given as force. You just take whatever the magnitude times cosine of theta and magnitude sine of theta. Those are your two components. Suppose we have a vector with magnitude 10, angle theta equals 120 degrees. Write the vector in component form and standard unit form. So the first thing I did here, you can use a trusted unit circle if you don't know these. The cosine of 120 degrees will be negative 1/2. And sine of 120 degrees is the square root of 3 over 2, right over there in quadrant 2. So in component form, you would take both those results and multiply them by 10 because that's your magnitude. So 10 times negative 1/2 would be negative 5. And then 10 times the square root of 3 over 2 would be 5 square root of 3. So that would be the definition of vector v. Or in component form, excuse me, that was component form. Standard unit vector form would be negative 5i plus 5 root 3j. And that concludes the video on vectors in the plane.